In section 6.3, we're going to be sketching graphs of equations that have an x squared either explicitly written or an x squared that would come out if we simplified the problem as its highest exponent. And each one of the graphs that we're going to do is going to have the shape of a parabola, and the parabola is essentially a U. And the U's that we get, the parabolas that we graph, are either going to be upside down U's like this picture, or right side up U's like that picture. You can generate parabolas that open left and right, but those aren't functions. We're not going to study those in this section. Ultimately, each problem in this section is going to be like the previous problem. For every single problem in this section, we're going to be given a function. And just like the graphing section for square roots and cube roots, we're going to make a table of values. We're going to sketch a graph. And then we're going to talk about some features of the graph. And the features in this section are parabola-specific features. And we need to talk about those specific features before we jump into the section so they're not new words to us. And they're not very complicated at all. So the parabola that I have drawn at the bottom of this page right now, which says the vertex of this parabola is the point 38, and the vertex of a parabola will either be at the very top of the graph or the very bottom of the graph. It's kind of the extreme point. It just depends if it's a right side up or upside down parabola. An upside down parabola, the vertex is at the top of the graph, and if the vertex is located at the top of the graph, the vertex is called a maximum point. Specifically because if you look at the y-coordinate of the vertex, here my vertex, it has an x-coordinate of 3 and a y-coordinate of 8. If I look at the y-coordinate of the vertex and compare it to the other points, like the y-coordinate of this point is 4, the y-coordinate of that point is -1, the y-coordinate, the vertex is called a maximum point because the y value of the vertex, regardless of whatever other points you might draw on this graph, the y value of the vertex is the very largest y value of all the points on the graph. There won't be a single point on the graph that has a y even equal to 8. Every other point on the graph, no matter how many points I might draw, their y's are going to be less than 8. So when the vertex is located at the top of a graph, we call the vertex a maximum point. And the verbiage that we're going to wind up using in the homework is something equivalent to this. When the vertex is a maximum point, I'll write a sentence similar to this. I'll say the maximum y value of all the points on the graph is the y-coordinate of the vertex, which in this case is y equal to 8. And this occurs when x equals to 3. We did that when we're doing local maximums and local minimums, so it's essentially the same thing. That's not necessarily new to us, but you might have forgotten how we said that. And as I get deeper into the section and I'm actually doing the problems, this nice sentence will degenerate into just a handful of words that have the same meaning, and that's kind of expected. One more feature of all parabolas is all parabolas have an axis of symmetry, and in our case it's going to be a vertical line that cuts the parabola into equal halves. I usually, when I graph my parabola, I draw in the axis of symmetry, and I did it with my program to draw this line, to draw the parabola. And this axis of symmetry, because it's a vertical line, and we know that the equations of vertical lines only have x's, the equation of that axis of symmetry is going to be x equal to some number, and it's the number that the graph goes through on the x-axis. In this case, it's going to be 3. So this parabola has an axis of symmetry of x equal to 3. When I actually get into drawing freehand, even though I'm using graph paper, my graphs, when I draw the axis of symmetry, it won't look like it has 2 equal halves, and that's expected unless you're just more talented than me. You can almost not be more talented than me when it comes to graphing parabolas. But if your line that goes through the vertex doesn't make it look like it has perfectly equal halves, that's understandable. The other kind of parabolas that we're going to do are right side up views. And in a right side up parabola, the vertex is located at the bottom of the parabola as opposed to the top of the parabola. And of course, we know that to be a minimum point. We called that a local minimum a few sections or maybe chapters ago. So when the vertex is at the bottom of a parabola, we call it the minimum point. And the reason we call it a minimum point has everything to do with its y. If you look at the y coordinate of the vertex, the y coordinate of my vertex is y equal to 1. And no matter how many additional points I draw, their y's will all be bigger than the y coordinate of the vertex. I only drew a couple points to make this graph kind of clean, but I could have put 100 different points on there, and every point that I could have put on there, its y wouldn't even be equal to 1. It would have to be strictly bigger than 1. And the nice, elegant verbiage to talk about the y value being smaller than the rest of the y values would say the minimum y value for all the points on the graph is y equals 1, and this occurs when x equals -4, just like we did when we were doing the local maximums and local minimums a few sections ago, or maybe even a few chapters ago. I kind of forget exactly when we did that. Been a long haul here. So that's the theoretical features that we need to identify. We also need to be able to recognize the types of equations that will produce parabolic graphs, or graphs that are parabolas. And there's 3 styles of equations that will produce parabolas. Very specifically, something that looks like this, which I call standard form, an equation that has, I don't really have room, something that looks like this. F of x equals some number times a parentheses with a plus sign in it or a minus sign in it. I don't really care so much about that. But something like that is going to graph into a parabola, specifically because if I cleared the parentheses, I'd get an x squared as my highest exponent. Similarly, I'll make a different function name. Something that looks like this will also graph to be a parabola. It doesn't have all the features here. It doesn't have a number after the square. That's not such a big deal. I could assume there's a +0 there. But both of these are written in something that I would call standard form. And parabolas that are written in standard form, when we go to graph them, we're going to graph them all similarly in terms of getting our table started. That was like when we graphed square roots and cube roots, the tables that I used depended on whether it was a square root or a cube root. When I'm graphing parabolas, the tables I'm going to use are going to be dependent on the form. Something like this that I call quasi-standard form, which is a made-up name. Something like 5x squared plus 3, or 7x squared minus 1. I'll call these quasi-standard forms, and all the problems written in this quasi-standard form will have a table that are similar to each other. And then the last form is a general form for a parabola, something like 6x squared plus 24x. I could have minuses in here, minus 12. The signs aren't so crucial, because any positive sign I could change to a double negative and make it negative. Any negative sign I could change into a positive if I do some proper math. So these are the 3 styles of equations or functions that we're going to ask to graph. The important thing is, if I give you an equation, to know what table to use. Generally, when I graph a parabola, I put 5 numbers. How about 5 sequential numbers in the x column? And I start my tables filling in the middle and working out. If I have a problem written in standard form or some variation of standard form, that's considered standard form, I would take the number in the parentheses and change its sign, put the number in the middle of the x column, and then increment up and down by 1. So if I was graphing f of x equals 3 times x minus 4 squared plus 5, those are the numbers in my x column. I'd start by putting 4 in the middle of my x column, and then I'd march up and down a couple. If I wrote something that's not quite standard form, but that's good enough for me, like negative 2 times x plus 5 squared without even the extra plus, this is standard form enough for me. When I go to make my table, usually I'll do a t-chart, but just to be consistent with what I have in the sheet, I'm going to have an x column and either a column with a function name or a column with the letter y. Just like this negative 4 turned into a positive 4 in my table, this positive 5 is going to turn into a negative 5 in my table. And then I'll get bigger than negative 5 incrementing by 1, smaller than negative 5 incrementing by 1. So that would be the table I would use for that negative 2 times the quantity x plus 5 squared. The quasi-standard form, the ones where they have a single x squared term without a parentheses, like if I gave you f of x equals x squared minus 8, if I just have a single x squared term, I don't have a parentheses, I use that table, negative 2 to 2. Now I'm feeling lazy. I'd put a 0 in the middle of my x column. I'd go up and down. In the last kind of problem, the general form, I need to use something from calculus to figure out my table. So if something has both an x squared and an x term, it's kind of the non-square root part of the quadratic formula is what I need, the negative b over 2a. So if I was graphing negative 4x squared plus 24x minus 5, I need the a and the b from the quadratic formula. And the number that I'm going to bury in the middle of my table's x column is found by doing negative b over 2a. I did the math here just to save some time. I'd plug that number in the middle of my x column, and then I'd go smaller and bigger. So let's just jump into the problems, because I've already spent a lot more time than you probably want me to, 13 minutes, doing nothing. So problem 2 that I'm about to graph is in this form, quasi-standard form. I'm going to use the negative 2 to 2 table to get my graph. And very specifically, for each problem, I'm going to make a table of values. I'm going to have, I can't even spell table. I'm going to make a table of values with 5 numbers in the x column. After I make my table, I'm going to sketch a graph. And then I'm going to identify the vertex. I'm going to state if the vertex is a maximum point or a minimum point. It has to be one of them. And then I'll make the appropriate comment about the y-coordinate of the vertex, saying that sentence. So I will state the maximum / minimum value, the maximum or minimum value in that little sentence. And I forgot I'm supposed to label the axis of symmetry. I'll put it at the end here. And then I'm going to state, I'm going to identify or draw in the axis of symmetry. And I'm going to get lazy and abbreviate the axis of symmetry as AOS, axis of symmetry. So because this equation is written in this standard quasi form. It's x squared, could be plus a number, minus a number. I'm going to use the table that has 0 in the middle and goes up and down by 1. So I'm going to use the table -2, -1, 0, 1, and 2. I'm going to use my calculator to get all the y's. The first y, I'm going to do g of -2 equals -2 squared plus 2. Heavy calculator section, so -2 squared plus 2, which is going to give me 5. Eventually, I'm not going to show much of anything. Just going to do everything on my calculator to save time. But at first, I'll show you what I'm entering. Second, I'm doing -1 squared plus 2. Third, I'm doing 0 squared plus 2. It's never wrong to have a parentheses when you're plugging a number in for a variable. If the variable is positive, you really don't need it in this particular problem. So this is just mindless. We've done this already. Must have entered this wrong. My tables have to have repetition in the y's. Let me redo this one. This -2 squared plus 2. Either I did it wrong or I wrote it wrong. One or the other. Something was wrong. I can tell my table is a good table if this happens. The number in the middle is different than the other numbers, and you have repetition above and below that number. If you don't get that repetition, you've made a mistake, and I found that mistake immediately. Very nice to have graph paper, and I just printed it out from that website that I used to create graph paper. So I see -2,6, -1,3, 0,2. Usually the middle point is the only point I actually show the coordinates on, because otherwise my graphs get too messy. 1, 3, and 2, 6. So now I'm going to draw the best I can something that's a curved U more than a V. And that's my making a table, even though I can't spell table, sketching a graph. And now I'm going to identify the vertex. The way I construct my table is the vertex is always dead center in that X column. This vertex, I can't spell, oh my gosh. This vertex is a minimum point because it's at the bottom of the parabola. It's actually a local minimum. It's actually even an absolute minimum, but for now, we'll say vertex is a minimum point. If you said local minimum or absolute minimum, more power to you. That's more correct. And then now I make the comment. I'm going to say the minimum y value, that's the smallest y value, is 2. If you look at the other points, their y's are bigger than 2. The minimum y value is y equal to 2, which occurs when x equals to 0. And then I need to make the axis of symmetry. It's going to be hard to see because it's located on the axis. There's my axis of symmetry. It's a vertical line that cuts the parabola into what's supposed to be equal halves. And the axis of symmetry, it always has the equation x equal the x coordinate of the vertex, because vertical lines only have x's, they don't have y's. I get a right side up parabola as opposed to an upside down parabola if the number in front of the x squared is positive. If the number in front of the x squared is negative, it flips it over. And I'm going to hunt out a -1 and jump all the way down to your problem 5. So if I want to do the same business for 5 that I just did, immediately I decide on my table. This is written in the quasi-standard form. It doesn't have a parentheses. It doesn't have both an x squared and an x term. I'm going to use the same -2, -1, 0, 1, 2 table. So to get started on number 5, first step is to make a table. I put 0 in the middle of the x column when it's in quasi-standard form. And then the y column I could call y, or I could give it a function name. The y-axis I could call the y-axis, or I could give it a function name. I don't need to write down every computation for my y. I'm just going to do them on my calculator. The first computation, I'm going to do -5 times -2 squared plus 12. So -5 parentheses -2 squared plus 12. My first y is going to be -8. And then, because this calculator makes it so easy, I'm going to delete that 2 and make it into a -1. So the next row of my computation, what I'm doing is just changing the x, and I'm getting a 7. And now I'm going to stop writing the work and just write the numbers down. Should get 12. Just mindlessly pressing buttons at this point. And then 7. And then 2. It's got to happen that you get this lovely duplication in your y's. If you don't see that duplication, you've made some sort of mistake somewhere. Either you don't have a good starting table or you didn't get a correct y. So let me plot. This is going to be an upside down parabola. The negative in front of the square gives you a maximum point with an upside down parabola. So -2, -8, -1, +7, 0 and 12. That's the only point I'm even going to label because it's the only point that I really need. And then 1 and 7, and 2 and -8. Not so good, but good enough. Not the best graph, but for me, not so bad. Let me draw that axis of symmetry in. It's supposed to be going right through the vertex. I've got a little issues there with my graph, but they're the best I'm going to do. So, have my table of values, sketched a graph. Now, I'm going to say the vertex is the point 0, 12. This vertex is a maximum point, which means the y-coordinate of the vertex is the biggest y value of all the points. So I made a table of values, I sketched a graph, I identified the vertex, I told you what kind of point the vertex is, and I'm going to say y equal to 12 is the maximum y value. If you look at my table, the 12 in the middle is bigger than the other y's, and it's bigger than all the y's of any point on this graph. So that would be the proper verbiage to describe the maximum point. The y-coordinate of the vertex is the maximum y value of all the points. It occurs when x equal to 0. And lastly, I need the equation for the axis of symmetry. And the axis of symmetry has an equation x equal to some number. It's always equal to the x-coordinate of the vertex. So I'm going to pause and we'll do a part 2 to this video where we graph the other kinds of problems.